Hello students, we observed the pattern of magnetic field produced around a current carrying straight wire in the last video. When the wire is straight, the pattern of the magnetic field is circular. That is, magnetic field lines are in concentric circles around the conductor with their common center on the axis of the conductor. You must have observed that the magnetic field is perpendicular to the conductor. We also know that if we increase the amount of current in the conductor, the strength of magnetic field increases. But is there any way of increasing the strength of the field without increasing the current? Yes, it has been found that the magnetic effect of current increases when the wire is converted into circular loop. So suppose this straight wire is bent in the form of a circular loop and a current is passed through it. What would the magnetic field look like? Let's understand it by an activity. Take a rectangular cardboard having two holes. Insert a circular coil having a large number of turns through them, normal to the plane of the cardboard. Connect the ends of the coil in series with a battery and a key. Sprinkle iron fillings uniformly on the cardboard and put on the switch. While current starts passing through the circuit, what do you observe? Yes, the iron fillings arrange themselves in a specific pattern. You can observe that magnetic field lines are in the form of concentric circles near the sides of loop or coil. But towards the center of the coil, the field lines become almost parallel, making the field in this part uniform. Students, you know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. Accordingly, at every point of a loop, the concentric circles representing the magnetic field around it would become larger and larger as you move away from the coil. In other words, the magnetic field is weaker at a distance from the conductor. This strength increases as we go closer to the center of the coil. Now that we know how field lines are around the coil, the question is, how can a greater magnetic field be generated around the circular coil or loop? This can be done by reducing the distance between two curves, that is, by reducing the diameter of the coil or by increasing the number of turns of the coil. Students, when talking about a loop or coil, how many turns of the coil are possible? A conducting wire can be coiled many times to have a number of turns depending upon the length of the wire. When a coil of many circular turns is wrapped closely in the shape of cylinder, the device is called a solenoid. In the case of a straight conductor, if we know the direction of the current, then we can find the direction of magnetic field using the right hand thumb rule. But will this rule work in the case of circular loop also? Yes, this rule will work for finding the direction of magnetic field of loop also. According to rule, hold conductor in your right hand such that your thumb points the direction of current in the loop. Then the direction of fingers wrapping the conductor is the direction of the magnetic field. By applying the right hand rule, we find that every section of the wire contributes to the magnetic field lines in the same direction within the loop. Right hand rule is also called Maxwell's corkscrew rule, which helps to determine the direction of magnetic field lines in this case. Corkscrew is a device which is used for pulling a cork from a bottle. It states that if we point the tip of the corkscrew in the direction of the current flow, then the direction in which the cork rotates shows the direction of the magnetic field, that is clockwise or anti-clockwise. Now let us see magnetic field due to solenoid. A solenoid is a type of device which is used to generate magnetic field by passing electric current through a coil having multiple turns. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the current carrying coil. The magnets so formed is called as electromagnet. Now look at the pattern of magnetic field lines around the solenoid on passing current. What do you observe? Yes, you are right. The pattern is the same as that of a bar magnet. So we can infer that a solenoid behaves like a bar magnet. In fact, outside the solenoid, one end of it behaves as a magnetic north pole, while the other behaves as the south pole. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is the same at all points inside the solenoid. That is, the field is uniform inside the solenoid. Strength of the field diminishes with distance from the solenoid. In fact, students, the strength of the magnetic field of a solenoid can be increased further by increasing the number of turns in the coil. Let's see how. This is because the current in each circular turn has the same direction, and the field due to each turn then just adds up. Also, each new loop in the solenoid contributes additionally to the strength of the magnetic field. So, the more the loops, the more the field lines. As a result, the field lines become denser, indicating higher magnetic field strength. Note students, there is no dependence on the diameter of the solenoid. That is, the field inside is constant. So students, we have learned that the magnetic field produced by a current carrying conductor can be increased by making it circular. Also, we learned that the magnetic field lines are concentric circles at every point of a current carrying circular loop. The direction of magnetic field of every section of the circular loop can be found by using right-hand thumb rule. At the center of the circular loop, the magnetic field lines are straight. Each segment of circular loop carrying current produces magnetic field lines in the same direction within the loop. The direction of magnetic field at the center of the circular coil is perpendicular to the plane of the coil, that is, along the axis of the coil. A solenoid is a type of electromagnet, the purpose of which is to generate a controlled magnetic field through a current carrying coil. The magnetic field produced by a solenoid is similar to that of a bar magnet. The magnetic field inside a solenoid is proportional to both the applied current and the number of turns per unit length.